Hello all, welcome to my seminar today on the topic tool wear mechanisms and types. It's a beautiful topic and very important also. So that's why before I start to present my topic, I would like to share some importance of this topic, that is tool wear. Generally we know that during machining we know that a tool is the very harder material than the work material, n times harder, because then only we could be able to shear off the work work material layer, and by layer method we could obtain the desired shape and size of our component. This is an idealized situation, but when it comes to real life situations, that is during machining, actual machining, we know that any material is not perfectly hard. That means every material wears out. It happens with situations. For example, some geometry, tool geometry would not be perfect. Sometimes tool material would not be perfect for the work material. It can happen in any situations, so that we should consider a tool wear, when it will wear and what will be the life of the tool before grinding or before throwing out, so that we would not be wasting the time in it, and the ideal time to machine will reduce, and so that the quality of the product and also cost of the product will increase and the cost will reduce. So tool wear is very important, because in short form I'll say that it will only decide the tool life and also the adaptability to the work material, because we can't say that HSS tool will cut cast iron, will machine cast iron. HSS tool is not designed to machine cast iron, so we should go for harder tools like carpets or nitrate tools or carbide tools. So material and geometry are very important to characterize the tool wear and tool life. Next slide. Let me start with an introduction, that there are three particular parameters which will decide the tool failure. First one is cutting force, and second one is cutting temperature, and third one is gradual wear. This gradual wear occurs with many mechanisms that I will discuss later on. Cutting temperature, as we know that if we increase the temperature of any material, that will decrease the hardness and the material will become very soft. This will improve diffusion and abrasion, etc. That I will discuss later. So as I said before, there are three modes of failure. Fracture failure, that means some irregularities in work surface, some bumps or some projections in the work surface will promote sudden stress rise in the work material and tool material. And this sudden stress, if it is not tough, the tool material is not tough, then the tool will fail, it will break away. It happens in local workshops. I have seen that many in local workshops, they do not consider these formulas. They just know some rule thumb rule, that is, for this material this tool will cut, but they don't know that the work material uh, will have some irregularities, and this will cause increased stress, and this increased stress can make the tool fail. So this is fracture failure. And temperature failure, I have said before, as I said before, temperature rise will promote softening of tool material. Gradual wearing is nothing but, there are certain mechanisms that I will introduce now: the adhesion wear, abrasion wear, diffusion wear, and plastic deformations. This type plastic deformation wear, these types of wears will occur at each and every time a component is machined. The tool will wear out by these mechanisms, and this is called a gradual wear. As gradual wear is promoted, it will decrease the tool life as it goes on. So we can characterize the tool wear types as two forms. First one is based on where the wear occurs. whether it occurs on flank or face or base or on shank. So there are basically two types in this one. The first one is crater wear and second one is flank wear that I will discuss now. As we know that in a tool geometry, if consider this as a tool, consider this as a tool face, this is end flank and this one is side flank, and beyond that we have a shank. This one is called face and this one is called side flank and this is called end flank. And we know that already, we know that temperature rise, the temperature maximum will have been taken place in this region, that is rake region, as we call this as face, but this face is called rake face. So that only we have considered rake angle, side rake angle and end rake angle, something like that. And this one is flank. As we know that it's a side flank and end flank. The cutting edge is this one. This is the cutting edge, and here only cutting happens. But as cutting progressively takes place, the chips will slide on this face. That's why the temperature is higher in rake phase. That we'll discuss now later. And importantly, the wear that takes place in this phase is called crater wear, and that wear which takes place in the edge near the flank, it is called flank wear. So, as I discussed before, three types of wear: due to temperature, due to sudden force, and due to gradual wear. Which is preferable? Gradual wear is always preferable because the wear, if it is gradual, it takes time to wear some, say, about few microns. It is preferable because the tool life will increase, and sudden fracture, the tool life goes out at that particular time itself. So gradual wear is always preferable. And as I said before, two types of wear are there. Threader wear. Threader wear occurs, as I said before, on the rake face, and it occurs mainly due to high stress and high temperature. It is due to the high temperature that is very predominant, because as I said before, the chips slide on that face, and so that the temperature will rise there and softens the material, and diffusion also takes place. What is diffusion? It's nothing but the higher concentration of the tool material is being transferred to lower concentration of work material, and this will reduce the material on the surface, and it is a gradual wear that I will discuss in later on. And the crater can be measured by either its depth or its area. Flank wear. Flank wear occurs at the side flank. Flank wear is predominant when we machine on hard surfaces and at low speeds. Why it is so? Because at high speeds temperature is predominant and it will create only crater wear. But at low speeds, what is predominant is the vibrations, and the cutting force is predominant. As the cutting force and vibrations are predominant, which only affects the flank, because cutting edge is here, it is near the flank. So as the cutting edge is nearer to the flank, at low speeds and at hard and cutting hard materials, the wear will be on flank. So it is flank wear. It results from rubbing between newly generated workpiece and flank adjacent to the cutting edge. Also, the predominant wear is nothing but abrasive wear. What is abrasion? Wearing away of soft material by a hard material. Why? Where is hard material? As we know, tool is very hard. Is workpiece also hard material? Yes, it can. I'll say a situation like after casting only we get the rod, isn't it? The work material. During casting, the casting sand sometimes will be inclusive into the work piece, and so that the casting sand is always very hard. So if casting sand is being deposited on the work material after casting, it will generally after during machining the if the sand particles hit on the flank, automatically the flank will wear out because sand particle is very hard than the tool material. Also, an important one point is that extreme condition of flank wear often appears at the cutting edge of the location corresponding to original surface of the work part. And this is also called as notch wear because the part where it wears has a shape of a notch, the V notch. You know, there are many types of notch, V notch, trapezoid notch, etc. So we can easily identify what type of wear it is. This is flank wear, and great. This is crater wear. This is a top view of the tool mid tool, and this crater wear we can see that it is gradually occurring, and due to temperature only we see this color difference. It is due nothing but the phase difference also we can say, and this is flank wear. We can see some fracture also has occurred in this part due to as I suggested that it's due to vibrations. This is flank wear and this is crater wear. You can see as in real life example. This is coming to the next important part, that is tool wear mechanisms. You have now understood that there are only two types of wear that can occur on a tool material, that is on the face it is called crater wear, and on the side flank it is called as flank wear. But how this occurs? We know that both are gradual wear and not due to sudden failure, it's gradual. So how this gradual wear occurs, what mechanism it follows? There are many mechanisms. Let me discuss it in detail. These are the tool wear mechanisms. The first one is abrasion, adhesion, diffusion, plastic deformation, and last but not least, that is chemical reaction. This chemical reaction generally occurs with materials which have higher chemical affinity. Example, you can say copper, aluminium, etc. The first one is in order of preference abrasion. See, what the abrasive wear is nothing but a harder material is scratching the softer material, and due to this scratching to and fro, this will promote ploughing of the soft material like this. It ploughs and takes away the work material, sorry, tool material. This wears are on the tool. How can a tool be so soft? It's due to two reasons. First one being, as I said before, sand particles will be there in the workpiece due to some improper casting, and these sand particles are very harder than the workpiece. Sorry, very harder than tool. So the sand particles will abrade the tool material, and it will abrade in the mechanism of ploughing, as we know that farmers plough the field with the help of uh, a tool. The same mechanism occurs here, but in a micro level. Occurs in both flank wear and crater wear. Yes, we know that Plank wear occurs due to vibrations. Vibrations are mainly important for abrasions to happen. So this will occur in flat wear. And crater wear, it occurs because the chips slide on the crater surface, and these chips will have some sharp sharp inclusions or the sand particles, and this will abrase the top face. The second one is about adhesion. Adhesion is nothing but at high temperature and pressure, the two metals are forced into contact, then they will weld together. That is not a permanent weld, that is a temporary weld which occurs. And this temporary weld, as is obvious that it will take away some material. For example, a material is here and another material, for example, this is tool and this is workpiece. A temporary weld has been formed here. As the sudden force increases, if the force is in this direction, this will take away, the tool will take away, because tool is very harder, so the tool will take away this work material. So it has taken away the material from the weld. As the weld occurs, sudden force, we are giving force, isn't it, for machining. So this force will break the temporary weld, and due to this breakage, some of the material from tool will be taken away into the workpiece, and this will promote weakening of tool and hardening of workpiece, and this is called adhesion. As we see here, as the chip flows, sorry, as the chip flows across the tool, small particles of tool are broken away and resulting in attrition of the surface. Attrition is nothing but hiding the roughness of the material. Smoothness will go off. The next one is about chemical reaction. Chemical reaction, as I said before, it occurs with materials with high chemical affinity, and the high temperatures and clean surfaces will promote these types of abrasion, these types of wear. Any material which takes up oxygen, that is, it is getting oxidized, then the material always weakens. This can be an advantage in manufacturing tungsten by atomization. We know that tungsten is converted to tungsten oxide, and and this will weaken the tungsten, and tungsten oxide is very weaker, and after breaking the tungsten oxide, again it is reduced to form tungsten. So it will be advantageous in some other ways, but it is disadvantageous, as we know that higher temperature will create more chemical affinity for the material, and this tool will get oxidized, tool surface will get oxidized, and this oxidized material will be very soft and very weak, and some small force will take away the material and shear away the material, and this is called chemical reaction wear. This becomes very important at high speeds and machining very harder materials. Next one is diffusion wear. Diffusion is the process of exchanging of atoms from higher concentration to lower concentration. What is the meaning of concentration is that higher chemical affinity, higher electrical affinity to lower electrical affinity. And also diffusion takes up during the some material will ionize and some atom will not ionize. It depends on the material, but it will take up the tool material and deposit on the work material. The same process is going on here also. The tool material will get harder and work material will get softer. As the process, it is also said that the tool surface becomes more susceptible to abrasion after this diffusion. It is, it's, it is true because the diffusion will be irregular on the tool surface and this will create irregularities on the tool surface, and these irregularities are the basis of abrasion wear. As you know that this irregular sorry these irregularities are the main key phenomenon for creating abrasion. So it is believed that diffusion is the principal mechanism of gradual wear. Last one is about plastic deformation. It occurs due to a particular parameter called cutting force. If cutting force is very high and along with that if cutting speed is also very high, then the temperature will rise and this temperature rise will soften the tool material, and the tool will deform plastically because as the material is softened, the cutting force, a small force is enough to shear away the tool material. So it is mainly contributed for the flank wear because flank is the place where cutting edge is there and cutting occurs. So there plastical deformation can take place. Tool wear growth. A general wear growth graph will be shown by me after this slide that suggests that how the tool wear is going to happen. There will not be, as I said before, there will be gradual growth of wear, but this gradual growth will have some different kinds of wavy graph. That is because there are some zones where the wear occurs. First one is breaking period, where the tool wears very rapidly at the beginning of this use. Within the few minutes of cutting, it will occur. And steady state wear is where the tool wear will be very gradual. If it is wearing at a rate of zero point 0.1 micron per minute, it will wear it gradually for about let's say 200 minutes. At last, there is a region called failure region where the wear rate accelerates at a high rate, and at suddenly the tool will fail or the tool will lose its shape. To be noted that the cutting temperatures are higher and the greater efficiency of the process is reduced. As I said before, these are the three zones: one, 2, and 3. These are the three zones where the wear rate is being depicted. The first zone, as we see here, that wear is at sudden high slope, and they are at a particular time. Let's say it is 1 minute time. For this 1 minute time, the wear rate is very high till here. So why this is happening? As we know that we are buying a new tool, but after buying a new tool, in a few minutes the wear is very high. Why is this happening? Because the tool as we buy will not have a complete smoothness on the surface. The smoothness will be very low, and this smoothness is very low, so that the wear rate will also be very higher until the surface gets totally smooth. As we know, during machining, the abrasion process occurs and the rough particles will wear away and make the tool very smooth. After the tool is very smooth, and we can see that approximately there is a gradual wear, and this uniform wear rate is the zone where most of the machining time occurs. At last we have sudden rise towards failure or towards the complete wear, that is called failure region. This is the condition where this is a time period where the tool life will go away and we need to regrind it, or we need to throw it out and buy a new tool. Today, cutting edge technologies have been developed and many changes have been in the market for diagnosing the machine tools. For example, this is a laser technology that is being used in milling and drilling processes, where the tool wear is being measured by using micron levels of laser. So we can say that it is very accurate in determining the tool wear, and approximately this is done in time machining, and this is the AFI imaging of a tool wear. This is done after machining. We can't do it during machining, but before image which I have shown that is in time machining, and real time tool wear inspection that is being done. So thank you all for listening to my seminar, and I hope that this tool wear and tool wear mechanisms and types will have been and very interesting topic, and thanking you all for this wonderful opportunity.